Well,
Thank you.
I'll start sharing my screen. Share, share, share. All right. Can everyone see that?
You're good.
Yep, we're good. We're live. All right, then let's do this. Ladies and gentlemen, and everyone watching, this is Game Development Patterns, an extremely self-indulgent talk. And I'm really happy to give it because I worked really hard on this presentation. We're basically repeating a presentation I did last year, but it's a good presentation. We have 69 nice slides of programming knowledge to cram into your brain. So let's get right into it. Oh no, I have to like click on the thing. I can't hit the arrow key. A prelude. What is this presentation and who is it for? So this is a programming focused presentation, and it's focused on giving some higher level knowledge to novice programmers unfamiliar with design patterns. You may know the basics of like C# or C++ at this point. You may be a more advanced programmer at this point. But you keep running into problems with your code, having to make weird workarounds to get features and systems to work in your games. And you end up abandoning projects or not having projects done the way you would like them to out of these technical frustrations. So if any of that sounds like you, this is your presentation. We're going to go through design patterns. So who am I? Who me? Well, I'm Kent. I am a fourth grader at RIT. I was lead programmer on a game called Overdrive. I made my own engine. I'm currently remaking that engine, and I am a certified cryptid. And I am currently treasurer here at RGDC, though that will change very soon. So here's the business. First, we're gonna go over what patterns are. I'm gonna make a little introduction for you, primed and ready. Then we're gonna go over some fundamental patterns, some basic ones, and how to use them, how to implement them. Then we're gonna do some behavioral patterns. This is stuff that helps you tell objects in your game what to do better. Then we'll look at some decoupling patterns. So basically, I think of these as organizational patterns, stuff that makes dependencies less common in your code, makes it much easier to optimize your patterns. And we'll talk about some optimization patterns outright at the end. And optimization patterns are pretty self-explanatory. They're just things that make the game run good. So, what is a game development pattern? Well, a pattern is more a solution to programming problems that we commonly run into. But more accurately, these are tools. Tools you can employ when necessary. These aren't exactly quote unquote solutions. Like they're more like building blocks that we can use to solve problems with. And employing them effectively is a really big part of the pattern. There's something to aid you when you're solving these programming problems. You shouldn't necessarily always throw them around in your code base just to have them there. And why do we use a pattern? Well, there are a ton of different reasons for why we would use a pattern, but for the sake of time, I don't have all day. It organizes your code. It makes it easier for other programmers who are also familiar with patterns to understand your code. It optimizes your solutions if you use patterns effectively. And honestly, it's just good software architecture. Like when I think about good architecture, what that means to me is that when I make a change, when I add a feature, it should feel as if the software architecture was made for that feature to fall right into place. And patterns really help us in getting to that point. Especially the stuff like decoupling patterns, which really separate your code and make it really easy to implement stuff. And that's really the essence here, is that patterns are things that we use to make our software better, more efficiently, and easier in our conceptualization of it. And what would I use a pattern for exactly? Well, there's all sorts of situations where you use patterns. These are just like a few: collision detection, rendering, AI decision-making, managing objects. Those are just a few, but there's like pretty much any aspect of a game or a game system, there's probably a pattern that will help you make it. That didn't help, Ken. I feel overwhelmed. I'm legitimately sorry if those did not help. All right, so now we're on to fundamental patterns. There's a few more patterns that I would call fundamental that I'm not going to go over this in this presentation. The ones we are going to go over are the command pattern, the singleton, and finite state machines specifically. There's a few others like observers, which are basically like the foundation of event-driven programming. There's prototype patterns, which are great for implementing wide-scale systems for many different types of objects in your program. And there's flyweights, which are basically a way to share super memory intensive stuff like 3D models between multiple objects. But for the sake of clarity and for the sake of time, I'll just leave you guys to look those specific patterns up on your own after this talk. Don't really have the time to go over them here in too much detail. So first pattern is the command pattern. And the Gang of Four, who I will be quoting and working off of this entire presentation, describe the command pattern as follows. Encapsulate a request as an object, thereby letting users parameterize clients with, yeah, this is a bad definition. I'm gonna tell you that this is not good. It's awful, actually. I don't know why they made this so obtuse. It's whatever like metaphor they're going for here just is completely lost to me. This makes no sense to me. It isn't English. So here's another thing they said about command patterns, which I think is just a better definition of it. Commands are an object-oriented replacement for callbacks. That's pretty good. But for this presentation, I'm going to make a definition for a command pattern that I'm borrowing from the book Game Programming Patterns, which is: a command is a method call made into an object. So how is this different than like a function pointer or a callback or whatever thing feature in your language? It's kind of like a function pointer. It's not the same. but sorry, is the chat window just like in the middle of the screen there? But like, it's just not the same. Let's just go into an example. So handling input is a great example of when we would use the command pattern. Somewhere in a game is a chunk of code that reads the input from the user, keyboards, mouse, controller, whatever. It takes each input and translates it to a meaningful action in the game. So a really simple implementation might look like this. We have an input handler that has a handle input method. If the X button is pressed, we make the player jump. If Y is pressed, fire a gun. A, swap. B, lurch ineffectively. Also, all code for this presentation will be in C++. I'm sorry, C# users. But everything in this presentation is also applicable to C# and other languages, especially when you're using objects and an object-oriented context. But so what if, instead of this naive implementation, I wanted to have rebindable controls? So we need to turn these direct calls that we have in our original code into something that we can swap out. We need some sort of object to represent that action. And in other words, we need the command pattern. And here is the starting of the implementation of that. So we make a base command class that just has some virtual functions. Most important to this is the execute function, which takes in an object as an argument. Doesn't have an implementation in the default command object, but that's not important because we're making child classes, and the child classes execute commands of the objects that are passed into them. It's much like an anonymous function in JavaScript, or how a lot of other object-oriented languages like Java and C# handle callbacks. So in our input handler, we're storing every button as a command object. And then when we are implementing the input again, instead of simply just returning nothing, it was a void function before, we're returning a command pointer. And we can see that if we're pressing a button, it returns the corresponding command pointer that then executes that command. So we can assign any command to any button. We can basically say, like, button X is the jump command, or it could be the fire command, or it could be lurch, or it could be swap. Like, it could be any of those. We don't really care in the context of our program. And that's what makes the command pattern so powerful, is that it makes it very easy to swap out and rebind controls at any point, even at runtime and before. So yeah, that's basically the benefit of the command pattern. I think you can kind of see why this would be beneficial. Next is the singleton. This is the most essential pattern for game development. If you're going to know any pattern, you're probably going to want to know the singleton, at least in the context of game development. For software development, they don't really like the singleton too much. But for games, it definitely has a lot of application that other software might not necessarily need. So The Gang of Four defines the singleton as ensure a class has one instance and provide a global point of access to it. So let's really try to understand this. Ensuring a class has one instance. Some classes do not work if you have more than one instance of that class. Some sort of external system that maintains its own state, a game manager that transitions between scenes, audio system that plays audio throughout the game, file systems, sometimes like particle or visual systems like loading in assets, things of that nature. They don't really work that well if you create, you know, multiple managers of them and then you're trying to keep track of, you know, 3 game managers. Like that would be absurd. So the second part, provide a global point of access to it. Several different things in our game are interacting with this system. There's only one instance, so it needs to be global. It cannot be a locally scoped object. Imagine if you had a game manager that you could not access from the level class. It just wouldn't really work very well. And so because it's global, it needs to be able to act asynchronously. Many different parts of our program are going to be interacting with it. So it may be getting tons of different function calls, and depending on how it's performing, it may need to order those actions. And then we cannot have any interference across different access points, which is why a lot of software engineers will tell you to avoid the singleton in more traditional software development context, because that specific point is really difficult for amateurs to kind of get their head around. Because if you're storing data in a singleton and then you're modifying that data and then you're accessing that data and you're doing things based off of that data, it can get really messy. The biggest suggestion for when you're using singletons, do not have data that you're going to be writing to. If you have an integer or any other data type that you need global access to and you need to modify it, do not put it in a singleton. Just make it some global variable. If it's absolutely necessary, that it has to be global. I would prefer you do that than stuff it inside a singleton. But with that caveat out of the way, a singleton is the solution to ensuring one instance and global point of access. So in this example, I will be walking you through a bare bones implementation of a file system. We know that the file system needs to keep track of its own state and that many of our systems will need access to it. So it's a pretty good candidate for a singleton. And here's what that might look like. So we have the file system class. It has a static function called instance. When it is called, it creates a new file instance file system in the file system pointer called instance. And once that instance is made, it doesn't get made again. It simply is called after we have created the class. So why would we use this? If we're not using the file system, it
does not create an instance of it. It's completely initialized and encapsulated at runtime. So this saves memory and CPU cycles, which is always a good thing. And since this singleton is initialized only when it's first accessed, it won't be instantiated at all if the game never asks for it. A common alternative to singleton is a class with a static member variables, and static classes instead of singletons are great when they're possible, but they're not always possible. There's one limitation to that static class, and that is automatic initialization. That initialization at runtime, otherwise called lazy initialization, is the solution to that. We don't have to worry that our compiler is going to initialize this static before our program is even called. And that has its benefits and drawbacks. Its benefits is that, again, saving memory, but the kind of big drawback is that this means singletons can't use information known only once the program is up and running. It also means that like singletons can't really interact with each other too much because the compiler does not guarantee the order in which static classes and singletons are initialized relative to each other. So if you're going to be using static classes and singletons together, keep that in mind, is that like interplay between is probably not a good idea, even between singletons and even between static classes. It's a pretty good point to keep in mind when you're implementing these sorts of things. And, oh, shoot. And another really powerful aspect of the singleton is that you can subclass it. Let's say we needed our file system to work across multiple platforms, for instance. To make that work, we want it to be an abstract interface for a file system with subclasses that implement the interface for each individual platform. So let's look at what that implementation could look like. So now we're looking at a PS4 and Switch file system. So we're implementing read file and write file for each of these particular classes, which would be part of the parent class file system. But each of those methods are implementing the Sony file API versus the Nintendo file API. And so you can see that, hey, we have some nice stuff here where like our file IO is handled entirely by one class. And if we're using the Switch and we're using the PS4, we know that this stuff is sort of contained. And the really clever part of making subclasses of a singleton is that when you create your program when you're building your program, you can set variables to be like, our platform is the PlayStation 4 or our platform is the Nintendo Switch. And based off of that, we can create an instance of the file system that is the PS4 file system or the Nintendo Switch file system. So we can make our implementation independent of the platform that we're using. Anytime you call the file system at this point, you don't really care in the rest of your program what platform you're using. You just call the functions that are part of file system. And it makes it so much easier to implement a lot of the features that you otherwise would have to kind of make a bunch of conditionals around. And so the final fundamental class is the states, specifically finite state machines. And for this, I kind of want to go into a bit of an exercise here. What is wrong with this behavior? Can anyone tell me? What is up with this? What is wrong? What is this assuming?
It assumes there's several different types of inputs
Uh,
or like different input variables.
I'm more thinking about the behavior. What happens? What is happening in this function behaviorally that is not good?
As long as you hold down button B, you're always going to be jumping up. I guess.
That's exactly it. There is nothing stopping the player from just mashing B and jumping forever. They're just gonna keep going up. So we add a flag and we make a flag that's called is jumping. And if the character hasn't started jumping yet, we let them jump. And then if they are, when B is pressed, they won't. Easy enough, pretty good. So now let's add something else. We want the player to be able to duck by holding the down button. So we're setting some animations in our button down state here. So what's wrong with this code? What's behaviorally, what is going on that isn't good here?
Well, the more functionality you add, it's gonna turn into like an if else nightmare, right?
Yes, that is the problem. That is the core problem. And that's basically the end of this, but specifically this code, there's a behavioral problem that where the player is holding down the duck button, which is down, and you can jump from the ducking position, and then you can release down while in the air in the middle of your jump, and then the animation will set to the stand animation while you're in the jump state, and it won't look right. So we have another bug, and in this one, and as Aditya correctly pointed out, this is an if-else nightmare. So we're just gonna stop. We're not continuing with this. There is something fundamentally wrong with this approach. Every time we approach this code, we break it. We haven't even gotten that complex yet. The player can't even walk in this code yet, and it's already breaking. So let's just throw this away and start over. The first thing we're gonna do, we're gonna document our states in a graph like this one. We have diving, jumping, standing, release, or sorry, diving, jumping, standing, and ducking, and then different ways of accessing each of these states. Well, congratulations, this is a finite state machine. We have a fixed set of states that the machine can be in. And the machine can only be in one state at a time. Our player cannot be jumping and standing simultaneously. Preventing that is one reason we're using the finite state machine. And that sequence of inputs, holding and releasing down, pressing B, pressing down while in the air. That series of inputs allows us to get to different states. And to show just like briefly in my game engine, there's a little implementation of a state machine. Basically, all of these are just functions that are assigned to visual elements in a GUI. So like you have the different edges, so you have different return statements, and then each of the states has different update methods that you can edit from this thing. But yeah, that's basically like the foundational part of a finite state machine. And this is using like real state machine stuff with like function pointers and assembling it. It isn't really a switch statement. It's quite complex in its implementation, and I'm not going to go over how I implemented that in this presentation. So there's many different ways to implement a state machine. There's enums and switches. There's the state pattern and dynamic dispatch, which are complicated, and there's static states, which I don't even want to touch at all. And then there's also other types of state machines. There's concurrent state machines, which are basically two state machines independent of each other with similar acting on one object, basically. And then there is hierarchical state machines, where certain states are set at higher priorities. And if a lower priority state and higher priority state are both in contention, it will always choose the higher priority one. And it kind of gets rid of a lot of arbitrary code you tend to get with finite state machines, where you have no real good way of transitioning between one particular state and another particular state. So you make like a third state that's kind of awkward. And hierarchical state machines kind of prevent that specific bottleneck. And then there's push down automata, which are state machines that kind of keep track of what states you have been in, and then you can roll back to previous states. It's really useful for stuff like network code and animation managers and certain use cases. But yeah, those are just a few of the different ways that you can implement and think about state machines. The one that I'm going to show you here is a pretty bare bones, easy to understand enum. So we have 4 states: the standing, jumping, ducking, and diving. And now we can handle our input by having a switch statement that looks at each individual state that we're in and handle events based off of that. When we hit the B button, if we're in the standing state, then we'll change to the jumping state and then insert the jump code there. If we're holding down the button in the standing state, we will do the duck animation and go into the ducking state. If we're jumping and then we're holding down, we'll go into the dive state. And if we're ducking and we release down, we will go into the standing state. So all of this is to make sure that we are handling our states correctly, and that just because you are in a certain state and you hit a certain button, you can handle input independently of all the other states. It's making our code more refined, easier to implement, easier to manage. Glad that's over with. We've made it through the fundamental design patterns, and now we can move on to the next set of stuff. So for this one, we got 2 quick ones: behavioral patterns, type object, and the subclass sandbox. These are patterns that help you quickly define a large amount of maintainable behavior. Type objects create sets of behavior without the rigidity of an actual class. Subclass sandbox gives us a safe set of primitives to build a variety of behaviors. So let's continue into more explanation and implementation. So type object, design problem. We have many different enemies in our game, and they all have associated data with them, strings, images, stats. How are we going to implement all of the enemies? So a traditional object-oriented approach would say to do this. We just make a parent class and have everyone inherit from that parent class. So we have a enemy parent class, and goblin, cryptid, and everyone else inherits from this enemy class. This approach is incorrect. Don't get me wrong, it works, but it ultimately gives you a ton of bloat classes that otherwise you wouldn't really need. There is a more optimal solution for this problem. Type objects. So what is a type object? We have two associated classes. That's it. Notice that there's no inheritance at all. With this system, each enemy in the game is simply an instance of the class enemy. The breed class contains the information that's shared between all enemies of the same breed. So to associate enemies with breeds, we give each enemy instance a reference to a breed object. To get any of the information, an enemy just calls a get method on its breed object, and the breed class essentially defines an enemy's quote unquote type. Each breed instance is an object that represents a different conceptual type, hence the name of the pattern, type object. What's especially powerful about this pattern is that now we can define new types of things without complicating the code base at all. We've essentially lifted a portion of the type system out of the hard-coded class hierarchy into data that we can define at runtime. We can create hundreds of different breeds by instantiating more instances of breed with different values. If we create breeds by initializing them from data read from some configuration file, we have the ability to define new types of enemies completely in data. So it's super easy. Some things to be aware of. We are now responsible for managing not only our monsters in memory, but also their types. We also have to make sure that all of the breed objects are instantiated and kept in memory as long as our monsters need them. Whenever we create a new monster, it's up to us to ensure that it's correctly initialized with a reference to a valid breed. We've freed ourselves from some of the limitations of the compiler, but the cost is that we have to re-implement some of what it used to be doing for us. With subclassing, you can override a method and do whatever you want. We could define an enemy subclass whose attack string changed based on the phases of the moon if we wanted to. You can't really do that in a type object pattern. Instead, we replace an overwritten method with a member variable. Instead of having an enemy subclass that calculates an attack string using different code than other enemy subclasses, you have a breed object that stores an attack in a different variable. This makes it easier to use type objects and to define type-specific data, but hard to define type-specific behavior. If different breeds of enemy needed to use different, say like AI algorithms, using this pattern becomes much more challenging. There are a couple ways we can get around this limitation. A simple solution is to have a fixed set of predefined behaviors and then use data in the type object to simply select one of them. So say we had like a standstill, chase, and runaway behaviors, we could like switch between those. And that fixed set of predefined behaviors is needed if you want to use different behaviors. So any behavior that you need in your type class, type object pattern, you need to define it beforehand in the original class. So there are just a few things to be aware of when you use this. It's really good for when you need to make a lot of very similar things. And for our implementation, let's build the breed class and then the enemy class. And we'll just handle two variables here, attack and health. It's basically just a container for our two data types here. You can see that the breed just has the health and attack variables. You can get them, you can set them. You can set them with the constructor and you can get them, but you cannot modify them once they are made. So it's pretty simple chunk of code, but it's the core of the pattern. Now that we haven't, now let's add our enemy class. You can see that our enemy constructor takes a breed object. So the health of our enemy is equal to whatever the breed's health is, and our breed is whatever breed we pass in. And then we can get the attack from the breed object, and then we would have other methods for taking damage and sending that attack out. But you kind of get the sense of what's all going on here. This is a very simple chunk of code, but it's the core. So moving on to the subclass sandbox. What do you do when you need a lot of classes with similar base functions, but entirely branching behaviors? So instead of a lot of similar behavior and a lot of different data, you have similar base functions, but entirely different behaviors. Well, that's what the subclass sandbox is for. So we use the subclass sandbox when the base class is able to provide all the operations that a child class may need to perform. There is behavioral overlap in the subclasses, and you want to make it easier to share code between them. And you want to minimize dependencies between those child classes and the rest of the program. So, Ken, this sounds like just having a well-structured parent class. It's a bit different in functionality. Let's look at an example. Superpowers. So we have a superpower class that has a virtual activate method and a bunch of functional methods for doing things like moving, playing a sound, spawning particles. The activate method is the sandbox method. Since it's virtual and abstract, subclasses must override it. This makes it clear to someone creating a power subclass where their work has to go. The other protected methods, they add that functionality. So let's create a subclass, a few of them actually. So this sky launch class, the first one, it springs the hero into the air, playing an appropriate sound, and emits a bunch of dust particles. So if all of the subclasses were this simple, we might not need a subclass sandbox, but you can kind of see the functionality here, right? We're moving, we're spawning particles, and we're playing sounds, something that like a lot of different classes might need to do. So implementing a more complex one, slightly more complex version of the same superpower, we get the hero's state by basically finding out where they are in the y-axis. So if they're on the ground, we can spring into the air. And then if we're like, you know, somewhere like in the air, pretty low to the ground, we basically do a double jump and we change how the behavior works. And then like way up in the air, we do a kind of like dive attack. So like you can easily modify the behavior of these subclasses, and you can see how you can get entirely different branching behavior based off of a ton of different variables and methods. And it's a pretty simple parent class, but you can see how that extends out. Finally, or well, not finally, we're at decoupling patterns. These patterns are for separating code and making it easier to edit. We'll be going over a component, event queue, and service locator. And first is the component. If you use Unity, do you guys use Unity? Do you guys use Unreal? That's pretty much it. That's pretty much the component pattern, but like it's almost exactly like how Unity uses it. Put behavioral objects, scripts, and patterns into add-on parts so that when one thing breaks, it doesn't entangle all of the other parts. Really quick implementation of that. We have a player class that has update methods for, well, an update method for itself, and then a bunch of other members that operate all the things that the player needs to do. So like input component handles the input, physics component handles the physics, graphics component handles the graphics. It's pretty straightforward. If you use Unity, it's pretty easy to kind of wrap your head around why this one would be so effective. Next is the event queue. This is a really complicated structure. And to put it into perspective, it's basically a queue that sends a ton of requests and then processes those requests. And that processing can be handled directly or handled in an entirely separate class that might be interested that like that thing happened. It's another really great pattern to know for event-driven programming. So first, we want to break it down. Storing a series of requests in first in, first out order. This is the queue part. When many requests are made, they are handled in the order they were made. This is a relatively common data structure, but I know everyone may not have taken like GDAPS or DSA quite yet. Sending a notification and queues the request. The request processor then processes the items from the queue at a later time. This means that while the requests are handled in order, the time it takes to handle them, we don't know. This lets us buffer everything, but not stop everything dead in its track when the event fires, waiting for it to process. And then requests can be handled directly or routed to interested parties, decoupling the sender from the receiver, both statically and in time. Basically, we're just ignoring or utilizing the events anywhere in our program. The object that sends the request and the object that acts on the events don't have to be the same and don't have to even be related to each other to work. An implementation of this would be way too time consuming to go over in this presentation. I encourage you to read up on it in the link provided in the presentation, which will be provided on the RGDC website. So the final decoupling pattern that we're going over is the service locator, one of my personal favorites. A service class defines an abstract interface to a set of operations. And this is a really long definition. It's a bad one too. Here's the better one. Provide access to functions without making an object that has the functions. Here's what it looks like. We have the service. We need to play audio. It plays, stops, and stops all the sounds. We have a service provider, which implements the actual part of the service. And then we have a locator, which finds the specific service that you're looking for. And in the code, this would look like we pass this audio pointer of the console audio to the locator. The locator gives us back that pointer anytime that we need it, as long as the locator is in memory. And then from that audio pointer that we get from the locator, we can access all of the functions. It basically makes it super easy to find functionality in your program without having to re-implement a ton of different functions over and over again in a ton of different systems. The final one, object pool, spatial partition. These are the optimization patterns. I'm going to basically skip the implementation altogether on these. They're both really complex. So an object pool is a class that maintains a collection of reusable objects. Maintain a fixed pool instead of allocating and deleting objects individually. This reduces memory fragmentation by a ton, which is a huge problem when you're working in C++. And it packs a bunch of objects together in an easy to manage area of the code. So if you want all your objects to do something, it becomes so much easier to make them do it. So why would we do that? Well, we use an object pool when we have a very large collection of the same type of object that gets used very frequently. Particle effects are the classic example, but you could also have enemies. You could also have notes in a rhythm game. And when I worked on Overdrive, we needed to make an object pool for that particular game because it would have taken so much more memory to put all of the notes dynamically in the memory at the same time. A very brief implementation looks like that. I'm not going to go over it. It's just a pool size that allocates particles, and then we're moving on to spatial partition. Store objects in a data structure that organizes the objects by their positions, which stores locality of objects relative to each other and updates the data structure when objects transform positions. Really efficient for object query near X location. Stuff like collision detection and audio sound effects are classic examples for why we would want to use that. So really brief implementation, we have a unit, we have a grid. Unit just has some positional data, grid adds units, and then you can check like what's contained within each of those units. Then the final design pattern I want to go over is a very dark design pattern. Parental discretion is advised. Like everything in this is, you know, if you're below the age of 60, you might want to just leave the room. This is the Kansas City air conditioner. And this is probably the most important software pattern you will ever learn. Our problem is that we need affordable air conditioning. The context is that we live in low-income apartments in areas with hot, humid climates, and the apartments have no casement windows. It's really important to have an air conditioner in the summer for comfort, but not for survival. Tenants can't install air conditioning and landlords don't want to. Room air conditioners are expensive too. Windows have optimal cooling, but some cooling is better than none. So the windows don't leak and we have all this stuff. All right, so what's our solution? Purchase an air conditioner, remove the entire window and prop the air conditioner on the ledge. Cover the rest of the window with a blanket or other material that provides an air seal for the air conditioning unit. That's our pattern. As you can see, this isn't a software pattern. This is satire about patterns. The big takeaway from Kansas City air conditioner is that design patterns are not the end all be all of solutions to problems. To reiterate, design patterns assist problem solving. They are not problem solvers. Take great care to make sure that the pattern fits the problem when you choose to use one. So many times I've seen cobbled together singletons, bloated subclass sandboxes, and inefficient space partitions. Kansas City air conditioner might be the pattern you need to remember the most. And we're wrapping up things here. We went through a lot today. I want to say I'm proud of all of you for sticking it out to the end. This is a hard presentation to make, and I hope you've all enjoyed it. It's a particularly dry and boring subject sometimes, and I hope I've been able to make it at least a little entertaining. But yeah, we're gonna wrap up here. That said, do we have any questions? Any like final questions? Like, is something just like really, like you really need an answer to it? If not, then here's a little bit of homework. I just want you to look at the resources I used in this presentation, especially game development patterns. I basically stole the entire presentation from that. And congratulations, we are done. Thank you, everyone. I'm really passionate about this stuff. If you have any follow-up conversations you want to have with me about this, I'm more than open. Thank you and good night. It's social time. Dane, do you want to take it away?
Yeah,
You can.
thank you. I just want to say this is available on our website and it's a lot of information, but if one of these problems comes to mind and you're thinking about the best way to solve it, you can always go back and check through the notes there and the links that Kent provided. So thank you, Kent. Yeah, I don't have anything to announce, so we'll just move into social time.